All right, I think this is good. Thank you for joining me here. I'm going to talk to you about a little language I've been developing at my place, Blockstream. My application here is cryptocurrency. And so I should give a little background of the motivation for the design of my language over here. So very quick background on Bitcoin. In Bitcoin, funds are guarded by small little programs written in a language called Bitcoin script. And a typical program in Bitcoin script, all it does is take as an input as a digital signature and validates that digital signature against the transaction data and the public key associated with that, those funds, right? So in Bitcoin, it's not quite true that you send money to people through a cryptographic public key, but you send money to programs. And it just so happens that some of these programs do this cryptographic check, right? But other more complex programs are available to be programmed in Bitcoin script. And we can do these things to create cross-chain atomic transactions, which allow you to execute a protocol that does a swap of currencies across different blockchains. We can build hash time lock contracts, which gives payment if somebody provides a pre-image of a hash within a certain time period, and you can extend this to do more interesting things so that the pre-image is a meaningful thing. We can build bi-directional payment channels where basically have a joint account with two people and an allocation of those funds between the two people, and those people can update their allocation of those funds offline so they can transfer money back and forth between each other without hitting the blockchain. And then the Lightning Network is a combination of the hash lock time contracts with the bi-directional payment channels put into a network to allow you to pay anyone that you can reach on the Lightning Network. And there's lots of more things we can do, right? So basically, the takeaway here is that Bitcoin is actually a form of programmable money. So very quickly, the way Bitcoin script works, right? It's got this stack machine. It has no looping constructs in it at all, right? So it's not Turing complete, famously not Turing complete. And this has some wonderful properties. It allows you to have static analysis of the Bitcoin script programs. In particular, you can bound the maximum number of each operation that is going to be evaluated before execution of the program. Because you don't have any loops, all you have to do is basically count the number of operations that are going to be there, right? And in particular, the Bitcoin protocol, it rejects programs that have too many expensive signature verification operations. So this prevents denial of service attacks because even before execution, we know how many of these expensive signature verification operations there are going to be. Bitcoin script allows the caching of results, right? Because in Bitcoin script, the evaluation only depends on the local transaction data itself in a Bitcoin transaction, right? It doesn't depend on the global blockchain structure. So that means that if you evaluate a Bitcoin script and you get a successful result, that result holds no matter where that transaction actually occurs in the blockchain, and it's other parts of the transaction data that will limit where it can occur. So these are all some very nice features of Bitcoin script, but it's not all roses, right? So there's a problem. Many operations in Bitcoin script were disabled by Satoshi Nakamoto, the creator of Bitcoin, back in 2010, right? So for instance, integer multiplication, not available in Bitcoin script. So this really limits the expressiveness of what we're able to develop for smart contracts for Bitcoin, right? So this is all a prelude to the motivation I have for developing a new programming language, right? So if I were designing a programming language for Bitcoin, right, from scratch, what would it look like, right? So we want to create an expressive language that lets users build novel programs and these smart contracts in a flexible way, right? We want to enable static analysis to bound the cost of resources of programs, and we want to provide formal semantics for reasoning about simplicity these programs using off-the-shelf proof assistant. So I call my new language simplicity. And in this presentation here, I'm just going to focus on the formal semantics of simplicity and reasoning about simplicity programs, so to illustrate how that works. Right, so this is Emacs, and this is the EGDA language that I'm going to implement simplicity in. I'm not an Emacs user, nor am I an EGDA user, so this will be fun for everyone. The syntax for EGDA is very similar-ish to Haskell, if you're familiar with that. And let me know if anyone has any questions about the syntax. So we're going to do an implementation of simplicity inside EGDA over here as an example. Right? So simplicity itself is a combinator-based typed functional programming language. Right? Let's do the focus on the types first. There are three kinds of types in simplicity. We have the unit type, which we denote by this little one over here. Right? It's the unit type. It has exactly one member of that type. Right? We have product types, A cross B. Right? So we have some pairing constructor that, given a value of A and a value of B, gives us our pair type for A cross B, and that's defined by this data constructor over here. And then we have disjoint union types over here, right? So we have a left tag constructor over here for A values and a right tag constructor for B values, and they both produce values of A disjoint union with B. So in particular, simplicity doesn't even have function types, which is a bold thing for a functional programming language. So is everyone clear with this notation for this? OK, good. OK, so let's start towards talking about the term language for simplicity. Every simplicity expression, T, denotes a function from some simplicity type that we define to some other simplicity type, right? So when we write for an simplicity expression T, we write T colon A turnstile B to denote that T is a term that has an input type A and an output type B, right? And so the semantics of simplicity is a function type, so we just define the turnstile to be a function, right? And it's important here to understand that simplicity expressions always denote functions, right? Simplicity cannot express values at all, because everything in simplicity denotes a function. All right, so the core simplicity language consists of 9 combinators, and they're on my shirt over here. Right, and I have the semantics on the back, so, all right. But let's go over the T-shirt in EGDA over here. Right, so we have an identity expression. Its input and output types are the same. We can give it semantics, and semantics is going to be the identity function. Now, you might be familiar with type inference, where if you give an expression, you can infer the type. But in EGDA, we also have program inference. So given a type, we can infer the program. So let's just do that. Right, it's the identity function. There we go. OK. The next one is the composition combinator, right? So if we have a simplicity expression S of type A to B, and a simplicity expression from B to C, then we can make a combinator that combines those two into a function from A to C, right? And that's just the composition operation. I don't know why it says no solution found, so we'll do it by hand. Like so. So that's the semantics of the composition operation, fairly straightforward. We have a unit expression that is a function that ignores its argument and always produces the unique value of the unit type, right? So that's just this lambda expression over here for the semantics. Next up is the pair combinator, right? So if S is a simplistic expression from A to B and T is a simplistic expression from A to C, what we can do is combine them together to get a function that takes an A and executes both S and T and pairs up their results over there. And that's what this function over here does. And we can, we can infer its semantics like so. The take combinator right? So if we have a simplicity expression from A to C, we can lift that into a simplicity function from A cross B to C just by ignoring the second argument of the pair and executing on the first argument, right? So EGDEG is going to need a little bit of help on here. So we're going to do a pattern match on the input like so, and it's going to return something, and that something is t of x, right? So we're just running t on the first component. Drop is very similar. It takes a simplicity expression from B to C and lifts that to a function from A cross B to C. And we can run the same game over here. We turn this input into a pair by pattern matching and infer the rest, right? So we run the combinator on the second component. The left injection combinator, ing_l, right? Given a function from A to B, we can turn it into a function from A to B union C just by tagging the output with the left combinator. Like so. So here we just run t and tag the result with the left combinator. And similarly, again, if we have a function from A to C as a simplicity expression t, we can lift that to a simplicity expression from A to B union C by using the right injection tag, like so. And then finally, the last combinator for the core simplicity language is this case expression. So this is really the only combinator that does any work. Right, so if we're given a pair and the first component of that pair is a disjoint union type, what we're going to do is we're going to do case analysis on that disjoint union type and then execute either S or T depending on which tag we have over here, right? So we're going to need, again, a little bit more help for EGDA. So if we have a sigma LA, comma C, then we return something. And also, if we have a sigma R B comma C, we're going to return something else, like so. And in the first case, we're running the S combinator on AC, and in the second case, we're running the T combinator on BC, right? Right. Okay, so that's it. And with these 9 combinators, we can write any function from a simplicity type to another simplicity type. This is sort of complete for this class of types that we've defined. So simplicity is meant to be a target language of some sort of language that you would describe your smart contracts in, right? But we're going to write some simplicity directly, even though we're not supposed to, just sort of to illustrate how the language works, right? So we're going to define the type of Booleans to be the unit type, disjoint union with the unit type. And we can't do values directly in simplicity, but we can create constant functions, which are a lot like values, right? So here we're going to create the constant function true. So we need to produce a disjoint union type. We're going to use the ing_right combinator. And it needs an argument that produces a unit type. And here we're just going to use unit to produce that output. And that's our definition of our true function, true simplicity expression. And we're going to define false the same way, except we're going to use the ing_l for false. All right. Let's get a little bit more sophisticated. We're going to put in a little syntactic sugar for the pair and composition combinators using the little triangle operator and semicolon operator, respectively. Let's build the not operation on bits, right? So we want to do a case analysis. And in the false case, we're going to return true. And in the true case, we're going to return false. And this doesn't type check, right? Because remember, the case combinator does case analysis on the first element of a pair. If we look here, the first element is not a pair. It's this Boolean type over here. So we're going to have to do something else beforehand. So what is that something else that we're going to do? Well, we need to build a pair. So let's build a pair of something and something. So the first component of the pair is the bit that we want to do analysis on, which is the input value over here. So we just use the identity combinator here. And the second element is just to be ignored. It's just to satisfy the case expression. So we're just going to plug a unit in over here. And right, so that all type checks, so we're good. Let's get more sophisticated. Let's do the OR Boolean operator. So again, we do a case analysis. Let's do the second case first. If the first value is true, then we can short circuit and just return true, like so. And in the second case, it's more sophisticated. We have this unit lying around that we need to drop first. So we'll put that in. And now we have the second bit over here. And so in the case that the first bit is false, we just return the second value over here. So we put an identity over here. And that's the definition of OR. OK, let's get really fancy now. Right, so we've had bits, right? Let's form multi-bit words, right? So we're going to recursively define 2 to the n bit words, right? So for 1-bit words, which is 2 to the 0, that's just going to be a bit, like here. And for 2 to the n plus 1 bit words, that's just a pair of 2 to the n bit words. So for example, an 8-bit word, which is 2 to the 3, is a pair of 4-bit words, which is 2 to the 2. And that's what this definition over here is doing over here. And now we can start going back to our digital logic course at undergraduate university. We're going to build a 2-bit adder. All right, so given 2 inputs, we're going to produce a 2-bit output. We have a carry bit and the result over here. In the first case, in the case the bit is 0, then there is no carry, so we return false, and we just propagate the second bit through for the second half. And in the other case, where the first bit is true, we have a carry bit if and only if the second bit is true, so that's why we have the identity function over here, and then we just flip the other bit over here, right? So that's the definition of a 2-bit adder. And we can make a 3-bit adder, which is called a full adder, which takes 3 bits and adds them to produce a 2-bit word. And so how does this work, right? So what we have is we're going to take the first pair of 2 bits, and we're going to recursively run, or we're going to call our adder function on those 2 bits, and we're going to hold the third bit for a while, so we'll do that. Then after that, so what we have here is we have the carry bit from our first addition, the result from our first addition, and our third bit's hanging around. What we're going to do is take the result and their third bit and add them together. So this function here grabs those 2 pieces over there and calls adder again. And here we just hold on to the first carry bit. And then, so now we have the carry bit from the first addition, the carry bit from the second addition, and the result of the second addition. And the way the full adder works is that if either we have a carry from either 2 additions, then we have a carry for the full addition. So we take those 2 carry bits and we put them together with OR, and then we just propagate our result to the second component over here, and that's what's going on over here. All right, so that's our full adder over here, but that was kind of questionable. Right, so is that really doing a full adder? So let's find out, right? Okay, so in order to know whether it's actually being a full adder, we need to understand what the meaning of these words are, right? Right. So the words, they mean natural numbers in some sort of Big Indian or Little Indian interpretation of the words, right? So we're going to write an interpretation function. And in the case that we have a single bit word that with the left constructor, that's going to denote 0. And if it has the right constructor, it's going to denote 1. And then if we have a multi-bit word, we have high bits and low bits. And the interpretation of that is the interpretation recursively of the high bits times 2 to the power of the width of the word, which is 2 to the n in this case, plus the interpretation of the low bits. That's right there. All right, and this is a specification for our full adder. It says that if we have bits A, B, and C, and we plug them into the full adder and we ask for the interpretation of that, that should be equal to the sum of the interpretations of the individual bits that went into the full adder, right? How are we going to do this? Well, there's only 8 cases that we need to consider, so we can just try them all to see if it works. So let's do that. And yeah, OK, they all work. And that's how we prove that. Maybe that was a little bit too easy. Let's make a ripple carry adder. All right, so we're going to take a 2 to the n bit word and a 2 to the n bit word and a carry in. And we're going to produce the sum as a 2 to the n bit word output and the carry out, which is another bit hanging out over here, right? And now in the case of a single bit input, that's just the full adder we defined already. So that case is just full adder over here. In this other case, right, what we have is that the first input bit has a high bit and a low bit, and the second one has a high set of bits and a low set of bits. So what we're going to do is we're going to take the low set of bits and the carry in, and we're going to recursively call full adder word on the low bits. Once we've done that, what we have remaining is the leftover high bits and the low bit of the result and this sort of intermediate carry value. And what we're going to do is, again, recursively call full adder word on this time on the high bits, and we're going to use that intermediate carry to propagate into the input over there. And then finally what we have is we have the carry out, the high bits, and the low bits, and we just sort of need to rearrange the brackets along these pairs to put everything into order. So we do that there. All right, so that's our full word adder. Now, did we really get this right? Let's try to find out. So we need a little bit more of a helper function over here. This is very similar to the meaning function we had before, which operated on words. But here we're going to operate on words plus a carry output bit over here. And the meaning of that word is basically the same meaning as before. It's the meaning of the y value, and then the carry bit is the sort of the overflow value of 2 to the n if it's set over here, right? So that's the meaning over here. And now what we're going to do is we're going to prove the specification of the ripple carry adder, right? And the specification is very similar, but this time instead of having bits, we have 2 to the n bit words A and B and a carry input C. And when you plug those values into the full word adder and we ask for its meaning, it means the same thing as the sum of the meanings of the words A and B and plus the carry input C. Right, that's the specification of a ripple carry adder. Right, so in the case of single bit inputs, that's just the full adder correctness lemma that we had before. So we've just rewritten that here. That works fine. And then I've put some preamble over here. Basically what we've done is that we have to prove this equation here is equal to this thing over here. And what we've done is, this stuff here is done is filled in some intermediate helper functions right here. So it says that we've defined C1 and R low to be the value of the subcall to full word adder word on the A low and B low inputs and in the initial carry input. And we've done the same thing for the adder of the high bits, right? So that intermediate value, we just defined C to be whatever the result of the carry bit of that operation is and whatever the result of that it is. Now, of course, these R low and R high, it's going to be the low and high bits of the result of the addition, right? But this is just defining it. We just know that it is a pair, and it's just assigning those values over there, right? So we'll be using that in our reasoning. And all right, so what did I say? Let's begin. We need to prove that something is equal to something else for some reason, right? QED. All right, so this is the thing that we need to prove is equal to this thing over here in order to get this to be correct. And now we need to give some reason. So this is a nice thing about functional programming is that we can do equational reasoning, right? So this is how we formally do equational reasoning. We cut and paste. Sorry. Emacs, help me out here. All right. All right, so we're going to make some intermediate step. And we're just going to start doing like high school math. So we're going to rearrange this B high over here, and we're going to like move it over here, and we're going to add them together like so. And then we're going to take this A low over here and move it over here. And add and put it together like so. All right. So that's our intermediate step over there, right? How do we prove this? Well, this is just true from high school math, right? So we say we need to solve a 6-variable high school equation with variables a high, a low, b high, b low, c, and z will stand for that 2 to the 2 to the n. All right, so it is true, it is obvious that a high times z plus a low plus b high times z plus b low plus c, that's obviously equal to a high plus b high times z plus a low plus b low plus c, like so. All right, that's obvious. Ta-da. All right, so let's just fill in these parameters. Like so. All right, first step is done. Next, we have this a low plus b low plus c, which looks suspiciously like this correctness lemma we're trying to prove. And so we're going to recursively call our lemma to rewrite that as this is really the semantics. This is the semantics of full adder word. Of a low and b low and c. We have to use our extended semantics there. All right, let's see how we're doing. Okay, so how do we prove that? Well, we need to use this conjugation to focus on some sub-expression that we want to prove. And so what we do is we use lambda expressions to define which part of the equation we're going to rewrite in. And it's going to be here. And what we're going to do is we're going to recursively call full adder word correct. And we pass in a low, b low, and c. See, that's fine. Okay, next we had this equation here that said full adder word a low, b low, c is just by definition of c1 and r low is equal to that thing over here. So we can perform this substitution of this eq1 equation to rewrite this term over here. So let's do that. So we're going to replace this with C1 R low. Good. And so the argument is very similar. We do a conjugation to focus on the part of the expression we care about, which is this, in this case, going to be within the meaning function over here. What have I done wrong? Oh, sorry, like so. And we're just going to use EQ1 in there. Perfect. Next up, the definition of the meaning of this pair is C1 times 2 to the n plus the meaning of R low, like so. And that just holds by definition, right? So we don't even have to give a reason why that's true. It's just obviously true. Okay, so no problem with that. And now a little bit more high school algebra. We're going to move this C1 over here, up inside the brackets over here. And get rid of this and move everything over here like so. Good. So why does that hold? Again, it holds by high school algebra. So I'm just going to speed things along by cheating, like so. Whoop. And I'll put that in there. And why did that not work? This is what happens when you're doing line coding, right? Well, let me come back to that in a moment and move on to the next thing. The next step is we have this A high. I think it'll become clear if I keep on working. We have this A high, B high, C1. And again, we can do a recursive call to rewrite that into full adder word of A high, B high, C1. That's within these semantics here. Sorry, full adder word. Right, and that again, we use this conjugation operation to prove that. And we have to give the context, which in this case is right here. And here, the proof is full adder word correct. Do a recursive call on our lemma. So this is on A high, B high, C1. And then, again, we do the same sort of rewrite we had before to replace this with C2. The meaning of C2 plus, times 2 to the n plus the meaning of R high. Like so. And again, we use this conjugation, except we're focusing this time within the meaning of this component. And here we're using EQ2, which is the second version of the thing that we were capturing before. Like so. And then finally, what we need to do is we need to pull this 2 to the n in in over here to refactor it and multiply these together, and we put in this 0, right? So there's like all these complicated reasons why that's true. And if you care what the reasons are, they are these reasons here. There you go, down here. All right, and like so. So other than my little gap that I've messed up over here, oh, I see, this bracket shouldn't be here. There we go, fixes that. And there, we're done. Right, so we have proven that our full ripple carry word adder is correct. It has the correct semantics over there, right? So welcome to my life. But this is cool, right? This is not something that programmers commonly do, right? They don't go through the effort of proving their program's correct. But it's something you can do with functional programming. And this is what I've been doing with simplicity. So I put on a GitHub my projects last night. And so you can find sort of information there. So like I said, I don't actually use Agda. All my work is done in Coq, and then I have sort of this Haskell like prototype. Like, of course, you can't do the proofs in Haskell. You have to do the proofs in Coq, right? So using exactly the same techniques that what I've described over here, I've written the SHA-256 compression function, and again, using equational reasoning, proven that the SHA-256 implementation in simplicity matches the semantics of the SHA-256 compression function as given by the verifiable C community. And this is nice because we formally verified the simplicity program, we can accelerate the evaluation in practice in simplicity, because when you encounter the SHA-256 compression function written in simplicity, what you're actually going to do is not do the interpretation in simplicity, but call into the OpenSSL implementation. And this proof of correctness shows that that substitution is going to be sound. Right, so there's like lots more to simplicity that I can't get to. So that's it for now. Thanks for your attention. Do we have time for questions? If there's a question, we have a little bit of time. Yes?
Do you think that Scala's type system can be used for somewhat similar kind of proofs? And if so, why? And if you don't think so, then?
So these proofs strongly rely on having dependent types, and that is something that Scala and Haskell and OCaml do not have, right? And so you really need, when you have GADTs, like we have in Haskell, I don't know about in Scala, right? You can get a little bit of the way there, but to really reason up code like this, you need the dependent types.
How about Dolly, like with the new version of Scala?
I'm not familiar with it, so I guess I can't answer.
Calculus that my understanding is that it tries to attempt something similar in Scala, but I don't fully understand it so far, so I'm kind of wondering to how.
Yeah, I'm not familiar, but yeah. All right, thank you very much again.